Okay, cool. So it's 2 minutes past 2 now. I think that's a nice time to start. So yeah, so very happy to welcome Samantha Buzzard today from Earth and Environmental Sciences Department. So yeah, as we were just saying, Samantha started as a lecturer here at about the same time as me back in 2021. Before that, a couple of postdocs was at Georgia Tech and UCL. So a little stint over the water before coming back again. But yeah, your PhD was in meteorology, right?
Yeah.
So you've been doing kind of like environmental stuff since the PhD at least. But you did maths before that,
yes,
right?
I am originally a mathematician.
So yeah,
it's nice to be able to talk about equations today.
Yeah. So that was at Exeter, right?
Yes. Yeah.
Yeah. So yeah, so today we're going to get all these Antarctic surface hydrology aspects and the mathematics behind that in Samantha's talk. So yeah, over to you, Samantha. Thanks.
Okay. Well, thanks for the introduction. Actually, my first slide was to tell you where I've been, so that's nice. I can skip that. But yeah, I was originally did a maths undergrad at Exeter. Did my PhD at University of Reading in the meteorology department, where a lot of people studying are either mathematicians or physicists, which is quite nice. Yeah, and then I've done kind of a couple of postdocs around in UCL for a bit over at Georgia Tech for a little while before I came back to the UK to take up my lectureship at Cardiff at the start of last year. So to give you some kind of context to this, it's quite nice, I guess, the science is probably new to most people in this room. This is a satellite image of what was the last and the ice shelf in Antarctica. So satellite image, we're looking down from the sky, dark areas ocean, white areas are ice shelf. To give you an idea of kind of the scale, these features here are mountain ranges. This is kind of a 10-kilometer bar there. So this was a very huge kind of area of ice, and I use the word was because shortly after this image was taken, we had this situation. So sudden and rapid collapse right across the ice shelf. The area of ice that was lost in just under a month was about twice the size of Greater London, so kind of a really big climate event. And this was probably one of the first times that our polar regions really made it kind of onto the news as a really, really big deal. This image was headlines, I think, in like the Washington Post, and it's certainly one of the first times where I kind of noticed this popping up in the news and thinking, oh, maybe this is a part of the planet that we should really care about because it's changing very fast. And the reason that we care about this is, of course, because other than, I'm sure people here may well have been watching the new Frozen Planet, we all love David Attenborough documentaries. We want to keep this beautiful, pristine environment nice for the penguins and the wildlife. But also in terms of an impact on us, especially being in Cardiff, we're in a city that's very vulnerable to sea level rise. And we can see that the contribution from both Antarctica and Greenland to global sea level is increasing at a rate of around 13 millimeters per decade. Now, you may notice there that Greenland is actually contributing more at the moment to global sea level than Antarctica, but Antarctica is kind of the one that we are really worried about because there's a lot more ice there, essentially. So if bad things start to happen to Antarctica, that's generally bad for the whole planet because, of course, sea level rise is going to impact us all. So one of the main questions my research is trying to answer is exactly how far is that arrow going to keep on going up? Now, I mentioned the term ice shelf, and because I am a mathematician by training, that's enough kind of satellite imagery. We're going to stick to a nice schematic now. And so ice shelves are the floating parts of Antarctica. So Antarctica is a continent that's mostly land covered by ice, but ice flows, it flows very slowly, but as it flows off the edge of the continent, we have these big floating areas of ice. And by big, I mean like what I just showed you, one that was twice the size of Greater London. Another ice shelf is the size of France. So large areas but floating on the ocean. So these are some of the parts of the polar regions that are most impacted by changes in the climate because they have the ocean underneath, so any changes in ocean warming, circulation, salinity are going to affect them from underneath. But also any atmospheric changes are going to impact them from above. So it's kind of been described as a sort of two-pronged attack that these kind of features are facing. And one of the reasons that we are kind of so concerned about them, not just because they're being impacted by climate so much, but because they prevent sea level. There's definitely a little bit of feedback, isn't there? I can kind of hear up here.
Yeah, sorry.
I don't know if there's anything I can do. I can edge this way a bit more, so I'm not near that.
Yeah, you can
I just don't want that to disrupt anyone on the Zoom. Sorry, what was it? So these ice shelves don't contribute to sea level rise directly because by Archimedes' principle, they're already floating on the ocean. So when they break off, like Larsen B did, it's not adding anything to the ocean that hadn't already displaced its own weight in the water. But what they do is they have a kind of buttressing effect and they hold back everything that's still on the continent. So take that ice shelf away, then all of that ice that's sitting on the land in Antarctica is free to kind of accelerate and will end up into the ocean and contribute to sea level rise. And this was noticed when Larsen B ice shelf collapsed and we got an acceleration of the glacier that previously fed onto the ice shelf and then consequent sea level rise. Okay, so ice shelves floating on the ocean. Ice shelves increase in density as you kind of go vertically down into them. So most of them are solid ice, but there's a lot of snow in Antarctica because it's quite cold, and that's how these ice shelves get replenished, is that snow falls on the surface and then that densifies over time to form something that's called Foehn, which I may also refer to it to. Foehn is essentially old snow. It's snow that survived one melt season. So you kind of have like light fluffy snow, denser Foehn turning into ice. And an important thing to note here is labelled up there as the pore closure depth. So this is the point where the Foehn hasn't fully transitioned into ice, but it is impermeable to water. So it still has air bubbles in it, but they have been kind of closed off, so water can't get below the pore closure depth. And that is kind of up to the point where I care about the ice shelf. I just care about this top part because my work very much focuses on the surface processes on the ice shelf and what's happening up there. And there's also important stuff happening in the ocean, but that's kind of whole different other research careers and people that care about that half. So when I be talking about the ice shelf from now on, very much referring to this kind of top part up to the pore closure depth. Okay, so back to Larsen B, how did those surface processes, how did they cause this ice shelf to potentially suddenly collapse, and why am I researching this? Well, if we look here at the kind of zoomed in area on the satellite image, you can hopefully see these kind of black features there. These were lakes that were formed on the Larsen B ice shelf, because Larsen B is located on Antarctica's peninsula. If you think of a map of Antarctica, it's kind of mostly round and there's a bit that sort of sticks out up towards South America. That's the peninsula, and because it's the most northern part of Antarctica, it's one of the areas that's warming fastest. Larsen B was located there. Its surface is melting, and in fact, just before it collapsed, it was covered in these lakes, huge lakes, kind of meters deep, even kilometers across, so really big features that are formed just from snow melting on the surface of the ice shelf. And what was noted when Larsen B collapsed is that these lakes started to drain. So first one would drain, then those around it, then those around that, in a kind of chain reaction that we think was kind of key in the sudden collapse of the ice shelf. But in addition to that chain reaction, we're concerned when we see these lakes forming because they're a different colour to the surface of the ice shelf. So they have a different albedo, they absorb more of the sun's energy. So when you get lakes, it's going to cause more melting as they absorb more energy. And also, if water gets into kind of existing crevasses on the ice shelf, then the pressure from that water is going to cause those crevasses to expand both sideways and downwards in a process we can refer to as hydrofracture, which can also be kind of key in these sudden collapse events. So how do these lakes form? Is a key question I tried to answer during my PhD research, because that is important in trying to work out essentially how they're going to spread to other ice shelves. It's a bit late for Larsen B at this point, but we're seeing them really all around Antarctica. So understanding how they form was a very key question to start out with. Okay, so there are three kind of basic situations. First of all, so we have snow up here, ice down there, the pore closure depth is where water can get to. If you get melting at the surface of an ice shelf, the water is going to percolate down into the snow. Quite a lot of that is going to refreeze within the snow because the snow is pretty cold, it's Antarctica, but some of it will get all the way down to the pore closure depth. Now, as it does that, and as it refreezes, it will increase the temperature of the snow around it because it releases latent heat. But once the snowpack has become kind of isothermal, so it's all at the melting temperature, water is free to percolate all the way down to the pore closure depth, then saturate that snow from the pore closure depth upwards, eventually leading to the formation of a lake. Now, in some places in Antarctica, this kind of snow Foehn layer could be tens of meters deep, so that's going to require a lot of water for this situation to happen. But Antarctica is not completely flat, so it's more likely that we're going to get some melting within kind of topographical lows in the ice shelf. but also water is going to move from higher points around the ice shelf into those lows, and that may make enough water in one place to get lakes. Now, the final kind of situation, and the one that I was really interested in investigating, was, well, what happens if enough of that water refreezes within the snow before it gets to the pore closure depth, that the snow gets really dense. And that process would be the formation of what we call ice lenses. So that's where the snow is cold enough water refreezes, we get solid layers of ice, and actually it doesn't matter where the pore closure depth is because the water can't get below these layers of ice, meaning that we need much less water to saturate the remaining snowpack above that to form a lake. Okay, so to investigate this, I started out by building a one-dimensional model for surface melt. The main thing to kind of take away from this, so it's a vertical column looking down through the snow, so it's kind of one dimension in that sense, but the kind of information on there around spatial and temporal resolution can obviously be changed depending on location and computing power. But the way that we force the model is through using weather station data, which tells us the surface conditions at the top of the ice shelf, or climate model data where weather station data is not available because Antarctica does not have a ton of weather stations, unsurprisingly. So now the bit I normally have to skip over when I talk in geography, so it's nice to finally be able to put the equations in and talk to people that might understand those. So the equation for the surface energy balance, every input here, starting with an F, is essentially information we get from the weather station. So latent and sensible heat, incoming shortwave and longwave radiation, and I use that to calculate a surface temperature gradient at the top of the ice shelf. So capital T is temperature and Z is height. I then use a heat equation to work out how quickly those temperature changes at the surface penetrate down into the ice shelf. And at the bottom, we just kind of have a no temperature flux boundary condition. But it turns out the boundary condition isn't super important because most stuff kind of happens way above the pore closure depth anyway. But I'll put that in there for kind of completeness to show you the whole model. So this is a fairly simple system of equations to solve. It's something that kind of, I guess, even during an undergraduate degree, you can kind of code up the heat equation and solve that and just have like a slightly more complicated boundary condition. But things get a little bit more interesting when we have melting occurring, of course, because then we first of all have the height change at the top of the model. So you have a moving boundary there. As snow melts, you will lose height. And we also get the density change within the Foehn, because when that snow melts at the top, it then percolates down into the Foehn and refreezes. So we get a change both in density and also in temperature because of the latent heat, which is released as that water refreezes. Okay, so using this model, I investigated the Larsen C ice shelf. So that's Larsen B's next door neighbour, and it's one that we're particularly interested in. So if I zoom into the satellite imagery here, you can see lakes present. Those kind of black smudgy features are lakes that are present on Larsen C's surface. So they're not as extensive as they were on Larsen B, but one of the kind of questions we were asking at this time was, well, how are these lakes forming? How much should we be concerned? Do we think they're going to migrate all over the ice shelf? And we're going to have a similar situation to the Larsen B ice shelf. Okay, so kind of initial investigations showed that we were getting density increases within the ice shelf. So here, kind of standard ice shelf density profile would essentially follow this curve down. So you can see that by running the model just for kind of one melt season or so, we got a significant increase in the density. So water was melting and getting down into the ice shelf and refreezing. You can see that here, looking at the water content of the model as well. So we're getting a layer of ice here, but also some water sitting on top of that. But this wasn't forming a lake. First of all, one of the joys of working in polar science is you often don't have data from the area you actually want to work in. And this turned out to be quite important for the Larsen C ice shelf because I was using weather station data that was located further down the ice shelf than where the lakes were present. So it was actually kind of reassuring that the model was not producing lakes because there weren't lakes there in real life. But I wanted to simulate lakes because that's what we were interested in. So the lakes are kind of up here. The weather station, I think, was around there. But one of the interesting things about the Antarctic Peninsula, especially, so maybe a real geography lesson today, is this kind of mountain range. And that is important because it produces things called Foehn Winds. You might also have heard these called they're referred to as Chinook winds in the US or katabatic winds, but essentially it's when air hits a mountain range and it's forced to go up and over the mountain range, you get a release of latent heat because some of that water is going to condense out due to kind of the compression or heating. And what it essentially gives you is this warm, dry, fast wind that kind of goes down the other side of the mountain range. And that's really important because these warm, dry winds are obviously going to cause quite a lot of melting. So those Foehn winds turned out to be really important. So we had to add in a Foehn wind effect to our weather station data. Thankfully, in the not so many years, I like to think, since I did my PhD, weather stations have improved. We've got some ones with actual Foehn winds, but for the sake of this work, we kind of just simulated a Foehn wind happening kind of every few weeks, matching the observations we did have. Okay, that wasn't quite enough to simulate lakes. The other problem being that the model is only in one dimension. Now, 1D models are great, you can run them on your laptop, they're really quick to code up. But if you're trying to simulate a feature like a lake, which is not in one dimension, then you do need to take that into account. So what we did, because we didn't want to move away from a 1D model because that would have been way too complicated actually for the time that I had in my PhD, was to essentially multiply up the melt that we saw happening in one area and assume that the surrounding area had similar conditions and assume that all that water was going to then pool within topographical lows. So essentially we had to estimate the catchment area of a lake. So if we think that all of this area is going to experience similar melting, I can say, well, how much water is within this white catchment area here is going to end up within the lake area. And we can double check that against kind of existing satellite data, just looking at kind of how much of an ice shelf was covered by lake and how much was covered by ice, and to check that we're getting kind of the right proportions there. And that allowed us to actually simulate some lakes finally. So first of all, looking at the temperature profile that these kind of changes to the model gave us. So on the y-axis here, 0 is the top of the ice shelf, negative numbers are looking down into it, and then temperature increases across the x-axis. You can see that all the way down to kind of 25 meters in the ice shelf, we had things that were isothermal at the melting temperature of ice. But probably more interesting was looking at the density profile. I'm just going to zoom in on the bottom there. You can see these kind of like squiggly features, I guess, or spiky features. Because you're mathematicians, I'm going to say now it's not an instability. We did go and check that because that was my first thought, and it's the first thought of pretty much everyone mathematically minded I've given this talk to, but we kind of checked it over lots of different resolutions. This was something that was actually happening. And this is very much like those ice lens features that I described. So we're getting these kind of solid pieces of ice forming within the pan of kind of different densities. And luckily, some colleagues from Swansea and Aberystwyth universities were doing some field work on Larsen Sea around the time that I was doing this work. So that allowed us to kind of compare what I was getting to what was happening in real life. So here we can see this is a snow pit that they dug in an area where lakes, they thought they were present in the past. So this is about 2 meters of snow pit. And what they did was they dug an identical snow pit exactly behind this. You had 2 pits of snow and a wall of snow and ice between them, shone a light through that, and you can see that these kind of spiky features in the density profile were very much present in real life too. So we're getting layers of ice, but between them kind of layers of foam that are not fully densified. So yeah, there's my lens, you can pick those out. But that was quite reassuring because often when you're modelling things that are as far away as the polar regions, you're kind of just doing your best guess and hoping it's right. So having something from the fieldwork that kind of backed up what the model was showing was nice, and that meant I could then go on to kind of add more complicated features, the lakes themselves, which is what I was really interested in. So,
quick question.
Yeah, of course.
Was there any sort of signature length scale that you could compare between your model and the data? In terms of the layers that you're getting?
Yeah, these lens structures, like
within the model, they're kind of dependent on the grid spacing that I pick. So yeah, that's a great question. But it's, yeah, they're almost a feature of the grid sizes that I was choosing. I think, am I explaining that well?
If that's true, then that's probably the model.
Yeah, it sounds like you could have.
If that's not
the
a
real
feature, that's a bug.
I mean, where is this noise? Like, it looked kind of like a bit random fluctuations that you say people thought might be an instability, but I mean, where's the origin of that kind of noise?
Okay, so no, I've explained that badly. Let's go back. So here, this is kind of, they look like this. If I make the resolution smaller, they kind of stay similar, but if I make it bigger, that's when then we lose them.
So yeah, as you make your spatial scaling, your simulation, they exist.
Mm-hmm.
So is there some kind of length scale in your vertical wibbles that you can compare to your data?
Yes, absolutely. So these, I guess, are kind of in the region of like 5 to 10 centimeters thick, which was kind of similar to what we see, but there's a huge variety within the ones that are seen in the field.
Do you have an idea, like from your model, the input parameters and their like dimensional units, how they control the length scale of these?
No, that's not something I looked into so much, because I was running this with not a huge amount of data, to be honest. So it's kind of, yeah.
It's just sometimes just dimensional analysis can give you a first hint. Anyway.
Yeah, no, that's a great question. Yeah. That's something, yeah, I would like to
something we can talk about after maybe.
Yes, absolutely. Yeah, we'll talk through that. So we get time to talk about the lakes themselves. So very similar model setup. But here at the surface, of course, we don't have melting because now a lake exists. So that's just kind of an incoming surface temperature based on the incoming solar radiation and weather conditions. And then we assume that the lake almost immediately is kind of fully turbulent and has a, what's the word? It's been a long day already. A uniform temperature profile, so it's well mixed, which matches what we have from observations of these lakes, the few ones that we do have. And then for the bottom boundary condition, we use a step-down problem because this boundary moves as the lake heats up. It will melt the ice below it, and this boundary can continue to increase the size of the lake, moving vertically downwards. And of course, this boundary is constant at the melting temperature. Okay, but being Antarctica, these lakes are pretty ephemeral. They tend to form lids of ice over them very quickly because it's quite cold there, just as it would be with lakes when they freeze here in the winter. But in the case of the lakes in Antarctica, we think that these kind of ice lids actually expand enough that they fully refreeze the entire lake throughout one season between the two melt seasons of subsequent years. And we model this using, again, a step-down problem to track that moving boundary between the lake and the ice lid. And very similarly to the original model, we have kind of a surface energy balance, and we use the heat equation to track energy transfer through the lid, but with the additional kind of Beer's law term in here, that's the 1 minus alpha term, because the lid is going to be transparent to kind of energy coming in from the sun, or semi-transparent to that. So some of that energy that hits the top will still make it down into the lake. Okay, and one of the findings, now that we can simulate lakes and look at them over lots of different years, is that refrozen lakes acted as these ice lenses in subsequent years. So as soon as you get one lake and it completely refreezes, then what you're left with the next year is essentially a giant ice lens within the Foehn, which means that the following year, you don't need to kind of saturate so much Foehn, you just essentially need to melt any new snow to form a lake. There's much less snow you need to melt. And that is shown in this plot. It's maybe just about good enough resolution to work it out, but the kind of bar is density. That way we've got time, and then down here is kind of subsequent vertical profiles going over time. So if you can make out this kind of triangular feature here, that is some water getting down into the snowpack, refreezing, increasing the density slightly until suddenly we hit where it turns yellow, is when we're getting kind of solid ice lenses forming and the water is saturating that Foehn all the way up to the surface, forming a lake, and that is all then refreezing before the next year. Just to say here, everything in yellow can be either solid ice or water. I haven't specified the difference between those in here because it just makes the plot really confusing. But essentially, this just shows everything that is either ice or is going to become ice as it starts to refreeze between the different seasons. Okay, and we could validate it at the time using some satellite imagery. So Landsat satellite allowed us to get lake depths, essentially from looking at how blue the lakes are determines how deep we think they are. We can do better than that in these days, but this is what existed kind of 10-ish years ago. And we found that our lakes were very much kind of falling into this part of the histogram. So yeah, maybe they were like a little bit deep, but not too far from what we were seeing, which was quite nice. And yeah, a whole lack of data really to evaluate that well at the time, which is unfortunate. We did do some sensitivity tests looking at the change in lake depth depending on the input parameters. So kind of unsurprisingly, it was most sensitive to air temperature and incoming shortwave radiation. Also, we did see that the lakes did affect the surface energy balance quite a lot. So if we assume that the lakes didn't form, so when I kind of showed that sort of way we like fudged having a lateral area around that, we could look at what was in the catchment area and what was in the lake. And there was around 70% less surface melt in that kind of catchment area. So that albedo change, that colour change from the lakes was really quite important. And we also found that the lakes that are forming on Larsen Sea at the moment are not that far from the depth where they don't refreeze between melt seasons, which was quite interesting. So I can show that here with just some very basic sensitivity tests of future climate scenarios here. So we both increased the air temperature by up to 1.5 Kelvin, and also the precipitation, which is in line with kind of climate predictions, how we think the peninsula is going to change over the next few decades. And you can see that in pretty much all these cases, it only took a very small change in temperatures, like half a Kelvin or 10% in precipitation, that the lakes were getting deep enough that they weren't going to refreeze between melt seasons, which was quite important because we thought that Antarctica didn't really have kind of perennial meltwater at that time, and it turns out it does, and that has since been spotted, we think, on the Antarctic Peninsula. Okay, so just kind of a very quick summary of that model, and the code is out there if anyone wants to use it. It's not a particularly complicated one-dimensional model to use. I kind of let master students do some small projects on it, but that has kind of all the processes to form lakes, all of the vertical percolation, ice lens formation, etc. And you can do some interesting sensitivity tests on that. But I kind of hinted earlier that we had to have a bit of a kind of fudge to get the lateral transport in to make something that resembled a lake, when actually Antarctica, of course, is not in one dimension. And we get features like this that have been observed since I did this work on Antarctica. So we can see here, this is on the Landsat ice shelf. There's not only kind of a fast-flowing river, but there's also a waterfall on the ice shelf surface. So these are important, first of all, because we think rivers could potentially be taking water to parts of the ice shelf that might be vulnerable to hydrofracture, but where we didn't think there was melting occurring. But also the waterfalls may be helping out the ice shelf in a sense that they're evacuating water very quickly from the ice shelf surface, meaning it doesn't get into those crevasses, doesn't form lakes, doesn't have those kind of negative impacts of the meltwater that we were seeing on Larsen B. And it turns out that there are features like this. Yeah.
So you mentioned before that the waterfalls can both help and hinder the ice shelf.
Yeah.
I know that in standard lakes, I'm not sure about these waterfalls, that fast-flowing water can pick up debris and start eroding stuff. Do we need to worry about that in this case as well?
Potentially. So a lot of this surface is just going to be kind of snow and ice, essentially. But the rivers themselves, just the water can be eroding within kind of the ice shelf. And that's something that I certainly plan to look at in the very near future, or hopefully my PhD student will be looking at it, because I think that's a really important question. But yeah, if in kind of areas of Antarctica where there is some kind of debris, then that could well be important, but it's not something, these kind of melty areas tend to be like very kind of slushy ice and snow areas. Yeah, great question, thank you. But yeah, so that's an example of one feature that may exist on Antarctica, but there are also tons of others. So there are huge lakes. This one at Amon Ice Shelf is 80 kilometers across. We've got subsurface lakes, as I mentioned, we've got waterfalls. So there's a ton of stuff going on that while a 1D model is interesting, it's just not going to cut it to really tell you what's going on in Antarctica. So this is why I created MONARCHS, which obviously has a terrible acronym because we wrote a grant that needed to have a word as a title. So it's the model of Antarctic Ice Shelf Surface Hydrology and Stability. And the reason that I kind of spent a good portion of the talk today describing the 1D model is this still forms a key part of MONARCHS, because we still need to have all those processes in there, that kind of ice lens formation and saturation and deferment. That's still really important to understanding where these lakes form. So we take these one-dimensional vertical column, we force the model with weather station or climate data, and then we essentially take an entire grid of these columns and move water between them. So that allows us to really concentrate on those small-scale vertical processes that are really important. So those ice lenses, as I was saying, they can just be like centimeters thick, but make a big difference to the lakes forming. But that also allows us to incorporate the lateral processes, mainly the movement of water across the ice shelf surface. But also kind of thinking my next kind of piece of work that I'm visiting Chicago at the end of this year to work on is ice shelf flexure. So essentially the loading of the ice shelf from all of that water can cause it to flex, and we think that may have been part of that chain reaction that caused RSB to break up. So we're planning to incorporate that into the model. And as I mentioned very briefly then in the answer to the question, channel erosion as well. So the model can move water around at different levels, so not just at the surface, but also at the subsurface, depending on where these ice lenses form and where water can get down to within that kind of vertical column. Okay, and this allows me to get a surface melt distribution for kind of any ice shelf really in Antarctica, depending on computing power and how much detail you want for any particular region. And the idea is that this will be then incorporated into larger ice sheet and earth system models. Because at the moment, our kind of big climate models, they have some ice in there, but not very well. They definitely don't model things like lakes on ice shelves or hydrofracture or any of those processes. So one of the next challenges is to work out how to get the information from models like MONARCHS into those larger Earth system models. What are those parameterizations that they need to take into account the parts of these processes that are then important for calculating future sea level rise? So a little kind of proof of concept of how we did the surface routing on the MONARCHS model. So here we just kind of have like essentially a Gaussian height distribution. So white is low, red is high, and then I added in kind of two little kind of lower areas into this and gave it a random water distribution to start with. And we would expect most of the water, of course, to end up in that main low in the middle, but also was interested to see what happens with those kind of two smaller lows at the side. They should fill up and overtop and end up into the main kind of lake in the middle, and that is exactly what happened. So you can always kind of see the trail here of water going from those lakes overtopping, and that's a process that's very much kind of been observed on, certainly in Greenland, that these lakes will fill up and then extra water will move around to kind of different lakes in a very connected system. And this is, yeah, just a very basic check that the surface routing was doing sensible things. It gets more fun when you give it a real digital elevation model and work with raw data. So this is Pine Island Glacier in West Antarctica. And we can see here the digital elevation model, again, darker areas are higher. So you can sort of see that the ice shelf itself already has these existing channels that have been eroded through kind of different periods of time, and when we give a water distribution, and then things do kind of pool within the topographical areas that we would expect, and then that system can then go on to evolve based on the changes in kind of temperature at the surface and albedo and so on. Another proof of concept, just because at this point I learned how to make GIFs and I thought it was quite exciting, for the Roy Bedouin ice shelf. And this was one that I was really happy. Sometimes digital elevation models in Antarctica can be affected by all different artifacts, but someone Sophie Berger, a colleague of mine, spent a lot of her PhD making a really good one for Roy Benoit. So this is a really nice example of an ice shelf that has a lot of melt going on, and one that we can kind of really validate MONARCHs' output against observations for. Finally, this was one that was particularly interesting because George VI ice shelf is on the Antarctic Peninsula, it's the same area as Larsen B and C, but it's one where loads of melt is going on. And at the start of 2020, we started seeing kind of images like this popping up within the kind of Earth Sciences Twitter sphere of people getting very excited about just how much melt was happening on George VI. My initial reaction to this was one slightly of panic because I had colleagues who'd been there just a few months before and had put loads of instruments on the ice shelf surface that I was hoping to get lots of data on to run MONARCHs with real data. But yeah, once kind of thinking about the weather stations probably floating in one of those lakes, after that I realised this is actually quite a nice chance to like run MONARCHs for this area as well and see kind of what features it was picking up and which it wasn't. So you can see here, first of all, hopefully in the GIF it's clear enough, but the George VI has this kind of like horseshoe shaped lake feature, and that very much comes out within MONARCHs. I think that is very much based on the topography of the ice shelf. But one thing we did notice is that up here we've got what looks a bit more like a river in the sort of orange yellow oval, whereas in the satellite imagery that's very much just a big lake. And I think this is a lesson in maybe not completely trusting digital elevation models, but also something that I'm hoping to look at in the near future to see if once we put those kind of flexure processes into the ice shelf model, is that going to cause more water to kind of pool in one area and get that lake forming rather than that sort of elongated river lake feature. Okay, so what is next? As I mentioned, river formation is a really important process, and that's something that we're hoping to look at future work in Cardiff. I can take lake formation and freeze up off because that's actually properly done now. And then ice shelf flexure due to water loading is kind of my next personal challenge that I'm going to be incorporating the existing module of ice flow flexure, coupling that with MONARCHs and seeing what it does. And if anyone is interested kind of in the more geography side, I did write an article for Physics Today earlier this year, which kind of explains all of this, but in a nice kind of way that is interesting enough for mathematicians and physicists, hopefully, to look at it, but still explains all the kind of polar science concepts that you may not have come across before. So yeah, if you feel free to take a look at that one if today's talk has sparked your interest at all. With that, I would like to say thank you very much for listening today, and happy to take any questions.
Thanks, that was great and clearly on time, so yeah, plenty of time for questions.
So when you went from your 1D model to the 3D model, so you took a combination of 1D models to make the 3D model. So,
yeah.
So what's the sort of scale up in terms of the number of 1D models that make up your 3D model?
It really depends on the area that you're trying to simulate. So one of the things that I found quite difficult with this initially is that the 1D model is, when you have lots of them, it's quite computationally heavy, because even though it's simple in itself, I'm running it over quite small length scales, kind of like 5 or 10 centimetre grid cells over kind of 40 metres of ice, which is what you need to capture the ice lenses, which are kind of so essential to working out where the lakes form. But then, yeah, having to work out a lateral scale, then that means I can run enough of those to capture the right topography and not lose that kind of fine detail, but also something that will run within realistic timescales was something of a challenge, but kind of settled at being able to do over kind of an entire ice shelf. The lateral scale is almost like hundreds of meters per grid cell. But if I'm really interested in particular features, then we can go down to tens of meters, but that is kind of looking at a very small part of the ice shelf. And that again, kind of that final GIF I showed of George VI, where I was kind of getting a river instead of a lake, that could very much be down to kind of the lateral scale of the model as well, because it's just too computationally heavy to do it on a finer scale.
Yeah, and the second related question then is, how do you sort of match the different 1D models naturally to get the connectivity?
Okay, yeah, so we start out, they have a kind of common base, but then they all have different surface heights. So everything is matched in relation to a height within the centre of the ice shelf, so a certain kind of height above sea level essentially is the base of the model. Then everyone has its own kind of different length scale above that, because the columns all change height as they melt. So when water moves laterally, the model will compare the heights of all kind of the surrounding columns, and it's kind of like I can't remember the name for it, but essentially it will find the column nearest it with the kind of the lowest vertical height and move the water across. The only time it gets a bit tricky is if more water is moving subsurface. So I have to kind of compare the heights of the grid cells and essentially move the water to the closest grid cell in the other, the next door column. But yeah, they don't, because they don't have the same heights. It's a bit, it's not exact, but we just kind of pick the closest cell.
Yeah, it looked just like your only coupling was on the boundary condition at the top. Would you say that you actually do some transport in the bulk as well? And is that just handled by like conservation of mass of the water, or?
No, it's so the water will actually, the model essentially kind of flags up which cell water can percolate down into. Yeah. So water is generally allowed to percolate down vertically as far as it can, because vertical percolation, in observations, we think is much faster than lateral percolation. We're still not quite sure, because we haven't worked out how to measure lateral percolation well yet. That's something I'm very much hoping my colleagues are going to be working on soon in Cardiff, because that's a really big open question in kind of snow and Foehn modelling. But yeah, we allow water to get down as far as it can, and then it will move laterally. And so it will then kind of look at the surrounding cells and say kind of which one is lower down, are there ice lenses there, can it move down, and so on. So yeah, it's the only coupling between the columns is the movement of water. I don't kind of do heat transfer or anything between those, because yeah, that would just be too expensive.
That would be a full 3D, fully meshed, like almost FEM.
Exactly, and no one has got hydrology in those kind of models for very good reasons. It's just, yeah, there's too much going on. We have those for pure ice and ice flow, but not hydrology.
In terms of currently where MONARCHS is, are you able to sort of close the loop to where you were at the beginning of the idea of this, catastrophic failure of the ice shelf flow? Can you get there yet, or is that sort of the next stage? Or?
That's the next stage. So there are people that are working on quite advanced fracture models that currently don't really think about hydrofracture, but are at the stage where they want to do that soon. So that's definitely another kind of future avenue of work. So there's some work funded at the British Antarctic Survey, where they'll be using MONARCHS to hopefully couple it with some of those fracture models and see if we can, see where that hydrofracture might be occurring.
And this flexing that you talked about, is that also going to feed into that? You can imagine, like, if it acts as a bulk which is under some extra stresses, then it's more likely to.
Yeah, absolutely. So that's a separate piece of work, but answering the same question, because depending on who you talk to within glaciology, some people will say kind of hydrofracture matters more, some people will say the inflection matters more, some people will say nothing on the surface matters, it's all about what's happening in the base. I try not to talk to those people. But yeah, it's still a very open question. It's like we didn't even really know that Antarctica existed kind of 100 and something years ago. Like if you look at maps from the 1900s, then you can see the edges of Antarctica, and in the middle it's just like, we don't know what's here. So in terms of an area of research, like we don't have loads of data, we're still kind of working on problems that maybe people in other areas of sciences have thought about a lot. So our hydrology models are way simpler than the field of hydrology, but yeah, it's just such a more challenging environment to work in with smaller amounts of data that there's so many open questions, which is great. That's why I chose to be there.